Think about this simplest way to make a decision. You flip a coin. It spins through the air, hits the table, and stops cold. It's heads or it's tails. There is zero ambiguity. Every piece of technology you use today operates on that exact same logic. Take your smartphone or your laptop, the servers hosting the internet. They all process information using bits. A bit is just a microscopic switch that can either be on or off, a 1 or a 0, heads or tails. To handle the immense amount of data generated by the modern world, we string billions of these little switches together. We build massive warehouses filled floor to ceiling with server racks just to process ones and zeros fast enough to keep up with our daily lives. But this binary system has a strict speed limit. Because a bit can only be one thing at a time, a classical computer has to solve complex problems linearly. If you ask it to find the way out of a maze, it has to trace one path, hit a wall, back up, and try the next path. It makes one guess at a time. Now imagine that maze represents the molecular structure of a new life-saving drug, or the physics of a virtual galaxy. The number of paths jumps into the trillions. The computer is still forced to check every single dead end, one by one. For problems of that scale, adding more server racks doesn't help. Even if a classical computer ran for the entire lifespan of the universe, it would never finish checking all those possibilities. To solve those massive puzzles, we have to throw out the classical rulebook and look at exactly how the universe operates at the smallest possible scale. We have to look at subatomic physics. Instead of the standard bit, a quantum computer uses a qubit. Imagine that same coin from earlier, actively spinning on the table. While it's in motion, it isn't strictly heads or tails. It is a blur of both possibilities at the exact same time. In particle physics, this fluid state is called superposition. As long as you don't measure the qubit by forcing it to stop, it holds a spectrum of multiple states simultaneously. When you apply that property to computing, the approach changes completely. A machine utilizing superposition doesn't trace one path, hit a dead end, and start over. It washes through every corridor at once, exploring all possible routes simultaneously to instantly reveal the exit. A classical computer reads a library by pulling one book off the shelf at a time. A quantum computer reads the entire library at once. But to actually process that much information, one spinning coin isn't enough. You need to link them together using a second rule of quantum mechanics. That rule is entanglement. When two qubits become entangled, they are permanently tethered to each other, even across physical distance. The moment one coin stops spinning and resolves into a state, the other one immediately resolves to match it. By chaining these spinning and tangled qubits together, engineers create a system where the processing power doubles with every new qubit added. They act as an exponential calculation engine, naturally canceling out the incorrect paths and amplifying the right answers. Because these machines use the actual building blocks of nature to run their calculations, they natively speak the complex language of the physical world. For healthcare researchers, this eliminates the need for decades of chemical trial and error. They can use quantum processors to precisely simulate how millions of different molecules will interact with a virus, streamlining the discovery of new treatments. That same modeling power applies to the human brain. By mapping the intricate structures and protein interactions behind neurological conditions like Alzheimer's, researchers can test treatments against a perfect digital copy of the disease. Outside the lab, this ability to sort through millions of variables at once solves massive logistical nightmares. Global supply chains can calculate the single most efficient shipping route across oceans, borders, and weather systems in real time. Even the hyper-complex data of global financial markets, driven by millions of fluctuating daily inputs, can be accurately modeled to predict economic trends and optimize long-term investments. Across all these industries, we are moving away from estimating best-case scenarios. We are gaining the ability to process millions of variables and find the exact right answer. In the digital space, this processing power provides artificial intelligence the ability to instantly render dense, photorealistic environments without the traditional lag of linear computation. This paves the way for digital media that flawlessly mimics real-world physics. Developers are already conceptualizing quantum games, where entire virtual worlds are mathematically generated with perfect physical accuracy. Now, none of this means your current laptop or smartphone is obsolete. For sending a text message, writing an email, or browsing the web, classical bits are still incredibly efficient and cost-effective. You won't have a liquid helium-cooled quantum processor sitting on your desk anytime soon. Instead, these machines will be accessed remotely through the cloud, called upon by researchers and engineers whenever they need to do the heavy lifting. They will run quietly in the background of our infrastructure, tackling the universe's most complex puzzles, one spinning coin at a time.